Evolutionary Intelligence. Mastering genetic algorithms with practical applications. Genetic algorithms, GAs, are powerful optimization tools inspired by the mechanics of biological evolution. By mimicking processes like mutation, crossover, and selection, GAs solve complex problems across domains ranging from engineering to artificial intelligence. This guide dives into the fundamentals, inner workings, and modern applications of genetic algorithms. Developers and researchers alike value GAs for their ability to navigate vast solution spaces without requiring exhaustive search. Whether fine-tuning hyperparameters in machine learning or designing efficient logistical routes, GAs offer a flexible framework adaptable to diverse challenges. Understanding their architecture unlocks new possibilities for problem-solving innovation. The foundations of evolutionary computation. At the heart of genetic algorithms lies a fundamental concept: survival of the fittest. Like natural evolution, GAs iteratively refine candidate solutions based on predefined criteria. Each iteration produces increasingly optimal results through selective pressures applied to populations of potential answers. This process begins with a randomly generated pool of candidates called individuals. These individuals represent possible solutions encoded in a format amenable to manipulation, often binary strings or numerical arrays. The quality of each individual determines its likelihood of contributing genes to future generations. In coding, solutions are represented as chromosomes containing genes that define characteristics relevant to the problem domain. Fitness evaluation. A metric quantifies how well each solution performs against the objective being optimized. Selection mechanisms. High-performing individuals gain priority in passing traits to subsequent generations. Recombination operators. Crossover exchanges genetic material between selected parents to create offspring. Mutation. Random alterations introduce diversity and prevent premature convergence to suboptimal states. How genetic algorithms operate step by step. A typical GA workflow follows a structured sequence of steps designed to progressively enhance solution quality. Initialization creates the first generation, after which iterative cycles apply selection, recombination, and mutation until stopping conditions are met. Detailed execution involves defining three primary phases: reproduction, selection and mating, variation, crossover and mutation, and replacement, maintaining population size. This cycle repeats until either an optimal solution emerges or a predetermined number of iterations completes. Initialization and population diversity. The initial population forms the foundation upon which all future improvements rest. Generating a sufficiently diverse set of candidates increases the chances of exploring promising regions of the solution space. Too much similarity among early individuals risks limiting discovery capabilities. Population size depends heavily on the complexity of the problem at hand. Smaller populations may converge faster but risk missing globally optimal solutions. Larger populations provide broader coverage but require greater computational resources to evaluate. Critical components shaping algorithm performance. Three essential elements determine whether a GA will succeed in finding meaningful solutions: representation schemes, fitness landscapes, and operator effectiveness. Balancing these factors ensures efficient navigation through potentially rugged search terrains. Representation choices significantly impact performance. Binary encoding simplifies certain mathematical operations but may struggle with continuous variables. Alternative representations like real-valued vectors or tree-based structures enable adaptation to different types of optimization tasks. Evaluating solution quality through fitness functions. The fitness function serves as the ultimate judge of candidate solutions' merit. It transforms raw inputs into quantitative scores reflecting proximity to ideal outcomes. Designing effective fitness metrics demands careful consideration of trade-offs inherent in most optimization scenarios. In multi-objective problems, traditional single-value fitness measures prove insufficient. Researchers often employ Pareto front analysis to compare non-dominated solutions when optimizing conflicting objectives simultaneously. This approach enables identification of sets rather than singular best options. Selection strategies driving evolutionary progression. Selecting parent individuals influences the trajectory of the evolutionary process. Various methodologies exist to prioritize superior performers while maintaining sufficient genetic diversity to continue discovering novel solutions. Roulette wheel selection gives higher quality candidates proportionally increased chances of reproducing. Tournament selection offers an alternative by comparing small random subsets before choosing winners based on relative merits within those groups. Elitism. Preserving top performers across generations. Implementing elitist strategies guarantees that the very best solutions never get lost due to chance events during reproduction. By carrying forward top-performing individuals unchanged, algorithms preserve hard-won progress made toward global optima. However, excessive reliance on elite members risks reducing population variance too quickly. Strategic incorporation of diversity-preserving mechanisms counterbalances this tendency towards premature convergence. Operators enabling genetic innovation. Two fundamental operators, crossover and mutation, facilitate the creation of new candidate solutions. While crossover combines features from existing parents, mutation introduces entirely new variations to maintain exploratory capacity. Crossover operates similarly to sexual reproduction, exchanging segments of genetic material between paired individuals. Different techniques like single-point crossover produce distinct patterns of inheritance depending on implementation specifics. Adaptive mutation rates for optimal exploration. Varying mutation probabilities dynamically enhances algorithm efficiency. Early stages benefit from higher mutation rates to promote wide-ranging experimentation, whereas later phases favor reduced values to refine discovered neighborhoods of good solutions. Some advanced systems implement self-adjusting mutation rates that respond to changes in population dynamics. Such adaptations help maintain equilibrium between exploitation, refining known good regions, and exploration, discovering uncharted territory. Practical implementation considerations. Translating theoretical knowledge into working software presents unique challenges. Successful deployment requires thoughtful decisions regarding data structures, memory management, and parallel processing opportunities inherent in GA workflows. Python provides robust support for developing genetic algorithms through libraries like DEAP and PYGAD. Leveraging these frameworks allows focusing efforts on conceptualization rather than infrastructure concerns. Tips for efficient code execution. Structuring populations as number PY arrays enables fast vectorized operations crucial for maintaining performance at scale. Careful implementation of selection and breeding routines minimizes unnecessary computations that could otherwise slow down large-scale experiments. Profiling tools help identify bottlenecks in custom implementations. Optimizing frequently executed sections reduces runtime overheads dramatically, making feasible even computationally intensive simulations previously thought impractical. Real-world applications across industries. Genetic algorithms find application in nearly every industry sector. From financial portfolio optimization to protein folding prediction, GAs consistently deliver innovative solutions where conventional approaches fall short. In civil engineering, GA-driven topology optimization improves structural integrity while minimizing material usage. In robotics, evolved control policies enable autonomous agents to adapt behaviors according to environmental stimuli effectively. Solving complex engineering problems. One notable success story involves aircraft wing design optimization. Engineers used GA techniques to discover configurations offering improved aerodynamic efficiency compared to traditionally manufactured wings. Similar methodologies have been applied successfully to optimize wind turbine blade geometries. Manufacturing companies leverage GAs for production line scheduling, achieving significant reductions in downtime costs. Automated layout planning algorithms utilizing evolutionary computation reduce waste and increase throughput in fabrication facilities worldwide. Current research frontiers and emerging trends. Ongoing advancements push genetic algorithms beyond classical boundaries. Integration with machine learning technologies opens exciting new avenues for hybrid intelligent systems capable of tackling previously insurmountable challenges. Researchers actively investigate ways to combine GA with reinforcement learning frameworks, creating systems that learn from experience while benefiting from evolutionary guidance. Such combinations show promise in dynamic environments where static rules fail to capture necessary complexities. Neuroevolution. Evolving neural network architectures. One particularly active area explores direct evolution of artificial neural network structures themselves. Unlike traditional methods relying solely on predefined architectures, neuroevolutionary techniques allow automatic discovery of optimal network configurations tailored specifically to target tasks. Pioneering works demonstrate successful application of these methods in computer vision, natural language processing, and robotic control systems. As hardware capabilities continue improving, expect wider adoption of these transformative approaches across many fields. Overcoming common implementation pitfalls. Newcomers often encounter difficulties related to improper parameter configuration leading to ineffective searches. Recognizing warning signs helps troubleshoot problematic behavior early in development cycles. Inadequate mutation rates commonly result in premature convergence, trapping algorithms in local minima. Conversely, excessively high mutation levels hinder progression by preventing useful traits from becoming established within the population. Balancing exploration versus exploitation trade-offs. Striking the right balance between exploring new solution territories and exploiting known good regions remains central to successful GA operation. Too much emphasis on either extreme leads to suboptimal results. Advanced systems employ sophisticated adaptive strategies that adjust exploration/exploitation ratios based on real-time feedback from ongoing evaluations. These dynamic approaches yield better overall performance compared to fixed parameter setups. Ethical implications and responsible usage. Like any potent technology, genetic algorithms raise ethical considerations regarding their deployment. Ensuring transparency and accountability becomes vital when implementing automated decision-making systems powered by evolutionary computation. Particular attention should be paid to bias prevention in optimization contexts. Unchecked evolutionary processes risk perpetuating or amplifying existing prejudices embedded within training datasets used to evaluate solution quality. Ensuring fairness in automated decision systems. Implementers bear responsibility for identifying potential sources of unintended discrimination hidden within evaluation metrics. Proactive measures include auditing fitness functions regularly and incorporating fairness constraints explicitly into the optimization process itself. Open sourcing GA implementations promotes scrutiny and collaboration that helps uncover blind spots. Community involvement fosters collective wisdom that strengthens responsible use practices across industries employing evolutionary computation. Conclusion. Genetic algorithms represent a remarkable intersection of biology-inspired computation and practical problem-solving prowess. Their versatility continues inspiring breakthroughs across scientific disciplines and industrial sectors alike. To harness this power effectively, practitioners should focus on mastering foundational principles before experimenting with advanced techniques. Continuous refinement through hands-on project engagement ultimately yields deeper understanding and mastery of these transformative algorithms.